So here's where things stand. There's some fairly robust statistical evidence that socioeconomic outputs of cities scale superlinearly with an exponent greater than 1. So we've seen income, GDP, number of new patents, quantities like this tend to scale with an exponent greater than 1, and many of these exponent values are clustered around 1.15. Many infrastructural properties of cities, total length of roads, length of water pipes, number of gas stations, tends to scale sublinearly, less quickly than linearly. If you double the size of a city, you don't double the length of the roads. It's less than double. So the exponent here is less than 1, and these exponent values tend to cluster around 0.85. So there's some empirical regularities that one observes. The question then is, can we explain these empirical regularities? Why do we see this pattern? And I'm going to discuss some thoughts along these lines in this video. So the situation was similar for Kleiber's law. It was well established that the metabolic rate depended on, scaled with a creature's mass to the 3/4 power. And then that begged an explanation, and the West-Brown-Enquist scaling theory provides a pretty convincing explanation for why that particular pattern, that behavior, is observed for the metabolic rate of animals. Is there a similar thing for cities? In my opinion, the answer is not yet, but I think we're getting close. So a relatively recent paper by Louis Bettencourt in 2013 puts forth a possible explanation for observed scaling in cities. And this is still ongoing work. I think it's not settled, it's not, in my opinion, fully developed, but it's promising, and it's certainly, in my opinion, interesting to think about. So in this video, I want to describe some of the elements towards this theory, some ways we might think about cities that could explain some of the scaling laws that we see. So our starting point, again, is going to be to think about networks. So for the vascular system, we said that the animals have to be served by a space-filling vascular network. So this is a obviously very crude drawing of this. It starts with a heart, and then it branches into 3, into 3, into 3. And this has to be space or volume filling, because every part of you needs to be served by the farthest out unit of this. There needs to be capillaries everywhere in your body in order to deliver oxygen and nutrients and to take wastes away. So an initial thought is to think about a city as also being served by a network. And I think that makes sense. We need sidewalks and then roads. We need water and electricity, and all of those are delivered to us by networks. However, the network for urban infrastructure may be self-similar, fractal, the way the vascular system is, but it's not a tree. So this is a tree because it goes and it branches, goes and it branches. It doesn't have anything sort of across like this. This is a very rough artist's rendition, or not very artistic rendition, of what urban infrastructure might look like. So the idea here is that this could be a really big road, maybe a highway. And then there are medium-sized roads. Those are these things here in blue. And then there's smaller roads here in red, or whatever color that is, and so on and so on. So we would see some sort of fractal or self-similar structure, sort of grids laid on top of grids laid on top of grids, but it doesn't have this tree sort of behavior to it. So, so we would describe it a little bit differently, just the sort of mathematics of it. Some other assumptions that go into this theory. So for the metabolic systems, we assume that capillaries are the same size in all creatures. And that, I think, is a pretty well accepted assumption based on the basic sort of biochemical properties that capillaries have to perform. And we can make a similar assumption here. It's probably not on as solid footing, But it seems fairly reasonable that, say for a water network, distribution network of water pipes, the smallest network, the smallest unit there isn't a capillary, but it might be a faucet. And it seems reasonable to say that the size of your faucet, size of faucets in houses, is independent of the size of the city. So in New York City or Beijing or Mexico City, some of the biggest cities around, faucets are probably about this big. I live in a really small town. My faucet is about this big. So faucets are about the same size everywhere. There might be a fundamental unit for transportation. If we're talking about sidewalks, it might be the width of a single person, right? Not in small towns, you don't have smaller sidewalks smaller than the width of a person. Everybody's doorway might be about the same. So anyway, so that's another assumption that might go into a theory of urban infrastructure. And then another network property one would think about is that if we imagine things flowing across here, again, we're going to have some conservation of flow. Flow conservation and optimization thereof went into thinking about this. And here also flow would have to be conserved. If these are cars, a road network, the amount of cars that flow in has to equal the amount of cars that flow out. Their speeds might be different. They might be a traffic jam. They'll be packed together. But flow in is going to have to equal flow out. So these all give us, these fairly reasonable assumptions, give us some mathematical tools that we can use to begin to think about how and why we might see scaling in these urban systems. There's some other assumptions or ways of thinking about cities that enter into the possible theory or explanation for scaling in cities that Louis put forth in this 2013 paper. The first is the idea that cities exist sort of to mix people up, that a city is mixing, that if you're in the same city, if we're in the same city, we can travel to see each other. The infrastructure network exists to do that. Maybe we live on different sides of the city and we don't see each other every day, but we could travel to see each other. And that extends almost from the definition of a city. A city is an agglomeration of people, a bunch of people living together that can all kind of travel to, from one side to the other, could at least in principle interact spatially. Again, the entire city doesn't mix itself up every day, but it's a mass of people that are somehow connected by some sort of a transportation network. So another assumption is that this transportation network, well, there's some costs associated with it as well, costs that might be related to socioeconomic outputs, and that would scale not with the area of the city, but with the transverse length of the city, how far it is to get from one side to another. So that sets up some scaling relationships there. Additionally, another consideration when thinking about cities that helps lead to some scaling results is that these infrastructure networks that I described previously grow incrementally. And they kind of, so you might have a network like this, and then a new house comes and it's in between two other houses, and then it's going to need water and electricity and maybe a path or a road to it. So networks, rather than sort of growing like trees, they grow incrementally and often sort of get filled in from the middle. So that leads to networks that get more dense over time. So that's definitely a difference from the tree-like networks that we have for vascular systems. So that's another consideration to think about in terms of how these networks play off of each other. And then the last assumption, or a key idea, and this is in some ways the most fundamental, is that socioeconomic outputs are related to interactions. So that what makes a city a productive place economically, culturally, is not just the mere fact that there are a whole bunch of people living close together, but those people interact. They share ideas, cultures, language, food, all sorts of stuff. And that in turn leads to certain types of productivity, new ideas in terms of new patents, additional economic activity, and so on. So one of the base assumptions is that socioeconomic outputs are proportional to the amount of local interactions people would have. So if you take those ideas and work with them mathematically, it's possible to come up with arguments for scaling relationships for cities. And in particular, there's an argument that suggests that socioeconomic outputs, patents, GDP, and so on, should scale as the population size to the 7/6 power. So that's a number that's a little bit larger than 1, 1.15, 1.16. That kind of tends to be around where many of these exponents cluster. Similarly, infrastructure network properties, length of roads, areas of roads, things like that, will scale as population size to the 5/6. So that's a number less than 1, about around 0.85, which is sort of around what we see. So, as I've said, this theory is still young. I think it's sort of the first steps towards a more solid theory. And I'm really interested to see how the theory progresses as people think more about the mathematics behind it and the assumptions behind it, where it leads over the next several years. To me, it's interesting to think about. I think it holds great promise. It's not as solid as the West-Brown-Enquist theory. It may not be able to be because cities are different than metabolic systems. But it's some interesting, sort of powerful, provocative ideas and shows, I think, some of what happens, some of the good things that can happen, interesting, thought-provoking things that can happen when some of these ideas of scaling and complex systems are applied to these complicated social systems like cities.